Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hi, welcome to Physics with Beth and Beth. I'm Beth. We're on this AP Physics 1 curriculum. We thought we were done with the videos, and then we had several of you out there request some review videos, so we were more than happy to help. If it helps you, we're willing to do it. So we are doing some review videos. We have just a few more coming at you in the next 2 weeks. But this one is going to be all about graphing, which I forgot to put on here. So we're going to review this whole graphing concept. Now, I will say there's going to be under descriptions, please note there's going to be some links, one to simple harmonic, how to interpret them, how to describe them, and how to create them, and from previous unit 7. So we're going to link those videos under the description. I would highly recommend you review those. And I would also recommend reviewing, I'll link the kinematics, how to take a position time graph and convert it to velocity time and acceleration time. I'll link those videos for that graphing video, for that graphing tips and how to do that as well. But let's get started on just a good review. We're going to remember that slope is rise over run. It's that old junior high formula that your math teachers used to talk about. What does that mean? Rise means the y-axis divided by the x-axis. We're going to really pay attention, not to memorizing, because there's too many different variables in all these to keep these straight. Don't keep that clutter in your brain when you don't need it. We're going to be using units and the variables on the y and x-axis to tell us what all these graphs are. And no need to clutter it with memorization, and during a high stress time like an exam, you can kind of get confused about those memorization things anyway. So we're just I'm gonna start, actually, we'll come back to this kinematics, but I'm gonna start with, we've got some forces here, we've got some impulse and change in momentum, we've got some work and power here. We're just gonna jump right in, and then some rotational as well. Okay, so we're gonna look at this force versus acceleration. Again, we're trying to figure out what's the slope equal to. So on this one, we're trying to figure out what the slope is, and that that straight diagonal line is an indication that it's constant. That slope is constant, but what is it? So well, we've got rise is acceleration, so I'm going to put acceleration on my rise, divided by my run, which is force. And you're like, oh, what does that equal? Okay, well, I'm going to go F, and an acceleration and a force, well, F equals ma. Okay, if I want to solve for this slope, I'm going to divide both sides by force. And then I'm going to divide both sides by mass, and I get 1 over mass equals the acceleration divided by the force. Okay, well, that's my slope. My slope is acceleration divided by force. Well, acceleration divided by force is 1 over mass. And it makes sense that that's constant, because in this, likely this was a lab, and you were keeping mass constant, but you were changing the force applied and measuring the acceleration, the change in acceleration when you applied more and more force. And as you applied more and more force, the acceleration increased, which again makes sense. But this slope is 1 over mass. So then if they're given a problem and they're saying, here's a graph, figure out mass from this graph, well, you're going to solve for the slope. Once you solve for the slope, then it's just the inverse of that is mass, because that's equal to 1 over mass. How would I solve for the slope? Well, let's say if this were 5 meters per second squared, and this happened to be 5 seconds, let's make it easy on ourselves. 5 newtons, making this easy on ourselves. Well, then 0 to 5 over 5, right? That would be your slope, how you would find slope. Your rise, it went from 0, let me just write this out. It went from 0 to 5, so it would be 5 minus 0, because final. It would be your final acceleration minus your initial acceleration. All right, and then you would divide that, let me put that over here, your final minus your initial. And then you would divide that by your final and your initial force. So we would have force final minus force initial, and that would be 5 minus 0. So that would be 5 over 5. So your slope would be 1. And that's equal to 1 over m. Well, in this case, that kind of works out nice, because then mass is 1, right? We could have probably made that a little bit more difficult for us. Maybe if I put, let's say this was 10 up here. So we'll do it a little easier. We have 10, our acceleration went from 0 to 10, our force went from 0 to 5, so that would be equal to 10 divided by 5, which would be 2. And so our slope is 2, well then 1 over m is equal to 2. Get that variable out of the bottom. I'm going to multiply both sides. And then mass is 1/2 or 0.5 kilograms. That's how you would do that. So find your slope and then recognize that slope is 1 over m. Okay, hopefully that helps. Hopefully you can figure that out. Now let's talk about torque. And I have torque versus angular acceleration here. And let me erase some of this nastiness that we just wrote all over the boards. I tried to give you a quick example of how you do this to find slope. But just take your farthest point and read what that is, and take your rise divided by your run. Now we have torque versus angular acceleration. We have same thing. We're going to do the exact same thing. We've got our rise is angular acceleration. Our run is torque. Well, okay, wait a minute. I remember that torque, Newton's second law for rotational motion, is torque equals rotational inertia times angular. It's going to be the same thing. We are looking, it's going to end up being 1 over rotational inertia equals that angular acceleration divided by torque. This is the slope, rise over run. So what is the slope telling you? It's 1 over your rotational inertia. Okay, and you're like, I don't understand why they couldn't have just put force on this axis and acceleration down here and make it easier on ourselves, and then the slope could just be mass then. Well, because remember in experiments, we like to put the independent variable on the x-axis, the dependent on the y. So we were changing force, and then the dependent variable was reading how it affected acceleration. So that's probably why. So method to the madness. We're not just trying to make your life miserable in physics. So anyway, now let's keep going. We have force versus time. Okay, this is area. We said, hey, area is rise over run. I'm going to look at this and I'm going to say, okay, my rise is force. My run is time. Oh, wait, I'm looking at my equation sheet. Force times time, that's impulse. All right, and we use a capital J for that. That's impulse. So the area under this is impulse. Now, we're also going to remember that impulse is equal to the change in momentum. So it's equal to impulse and change in momentum, because impulse is always equal to change in momentum. So that's the area under this. By the way, if you were doing this problem and they said, hey, find the change in momentum, or maybe they wanted to find a velocity from that change in momentum, divide this into a triangle, and a rectangle, and add up the 3 areas. Easy peasy. Okay. Now, torque versus time. We're going to run into the same thing. I'm going to take area. So let's say I have, let me do this again. All right. So I have torque times time. I'm just taking rise times run. Oh, torque times time, that is angular impulse. So this area under here is equal to change in angular impulse. I'm sorry, is change in angular momentum or angular impulse. Let's get that right. And angular impulse is the capital J, and you can put a little A and G for angular. But again, we know that angular impulse is equal to that change in angular momentum. So that's what torque times time is. So that's what both of those are. Again, you could do 2 triangles and a rectangle. Now, I want to show you force times time. We know already that this is impulse or change in momentum. They equal the same. But what happens if you have a line like this? Well, this is positive, and then this little rectangle would be negative. So don't forget that. If it's below that 0 line, then that area under the curve there is negative, and that's positive. You would add that, you would subtract that from that to get your total impulse or change in momentum for that problem. Okay, now let's go to force versus position. Force versus position, I'm going to do that I'm going to do the area again of rise times run. So what is force times position? Oh, I'm looking at my equation sheet. That's work. All right, so I know that's work. So that means the area under this is work. How can you do that? You've got a triangle there and a rectangle, and both of these added up would be your total work. Torque times angular displacement. Okay, well, same thing if we had something that looked like this. Torque times your angular displacement. Oh, we know that. That's on our formula sheet. That's also work. And both of those are in joules. So that's going to be your work again. It's just going to be work from something that's rotating. Okay, now we go to work time, this work time. Okay, I've got a line here, and what I'm asking for is what's the slope? Again, rise over run. So we have work divided by time equals your slope. Well, work divided by time is power in watts. So that slope on that line is power. And in this case, you would have constant power. How do I know that? Because it's not a curved line. It's a straight diagonal line. So that is the concept of using slope and area to figure out what they're giving you and what you can interpret and what you can calculate from your graphs. All right, you don't have to memorize all of these different axes and which graph and what's the slope or what's the area. Use this area as rise times run and look at your variables all the way through. Okay, now we're going to go to kinematics now really quickly. I'm going to start here with a free fall. I have 3 scenarios. I'm dropping, I'm throwing it down, and I'm throwing a ball up, and then it falls down. All 3 of these are velocity time graphs. All right, I have velocity on the y-axis, time on the x, and then I'm going to recognize that, hey, if I did this acceleration time graph for all 3 of these would be exactly the same. All right, because if I did an acceleration of meters per second squared and time in seconds, free fall acceleration due to gravity is always negative 9.81 meters per second squared as long as you're calling down negative, which we are. So it stays the same as long as you're on Earth, right? Now, yes, if you go higher up, it's going to be a little less, whatever, but our average is negative 9.81 on Earth. You go to the moon, something different, right? But we're going to do all these on the Earth. Well, they're all going to look the same then. You're going to have a straight horizontal line because that means constant acceleration. It's not changing. And it's going to be at negative 9.81 meters per second squared for a free fall problem. But what does the velocity time graph look like? Well, if you drop a ball, your initial velocity is 0. You just have it here and you drop it. But your acceleration due to gravity is still negative 9.81 meters per second squared. So it's going to start at 0 velocity on that 0, 0. It's negative and it's negative constant, so it's going to look just like this. And this is going to be a negative 9.81, and that is a negative slope there. Negative 9.81 meters per second squared is going to be that slope. Now, let's look at what's happening at velocity. It makes sense because if you drop it, it's at rest, but then it gets faster and faster and faster as it falls. So your velocity is like negative 1 meters per second, negative 7 meters per second. It's getting bigger. It's just the negative just means direction. So negative 7 meters per second is greater than negative 1 meter per second because you're just looking at 7 meters per second versus 1 meter per second. The negative just means direction, so don't let that confuse you. Now throw down. You throw down a ball. Okay, so we're throwing down a ball, and I have it, and I throw it down. That means I'm giving an initial velocity that's negative. I'm already starting. I don't care. Let's say it's negative 3 meters per second. So I'm going to start here at negative 3 meters per second. And I'm still going to have the exact same slope. I'm trying to make those parallel because it's still an acceleration due to gravity of negative 9.81 meters per second squared. It doesn't matter if you throw it down, you drop it, you throw it up. The acceleration due to gravity is always the same, negative 9.81 meters per second because it's down. So the slope is negative 9.81 meters per second squared. All right, now what happens if you throw a ball up and then falls down? A lot of people want to say, oh, I know, it looks like this. You throw it up, it comes down. No, that's not quite right. No, 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 as we used to say in my class. No, no, no. You are throwing up a ball and then it's coming down. So what happens is on the upside and downside, you have positive velocity. It goes to 0 at the top. Why? Remember in free fall, stops to turn around. That split second, it'll stop to turn around. And then you have negative velocity on this side. This side, it's slowing down. Because you have some positive velocity and it gets less and less and less and less till it gets to 0. On the downside, it starts at 0 and it gets faster and faster and faster until it comes back to whatever, if it's the same height, whatever velocity it started with. So it's getting faster and faster. So here's what it looks like. You start at positive velocity. Let me erase some of this because this is over here kind of in the way. All right, so it starts at positive velocity. And then at max height, velocity 0. And then on the downside, meaning it's going to have negative velocity, it's going to be speeding up. So I throw a ball up and then it falls down. It starts at positive velocity. It comes down to 0. Right here is max height. That's max height when it hits 0 velocity. And then it starts speeding up. So look, here it's slowing down, just like we said it would slow down. Maybe it starts at, I don't care, let's say it starts at negative 20 meters per second. Then it goes to positive 20 meters per second because we're throwing it up. That would be positive. And then it starts slowing down, 10 meters per second, 5 meters per second until it gets to max height at 0. It stops to turn around. Now it starts speeding up. It's at negative 1 meter per second and then 10 meters per second. And eventually at the same height, it'll go back to its negative 20. And guess what? I tried to draw these all at the same exact angle. I'm sure I didn't do a great job, but I tried because that's acceleration due to gravity, which is negative 9.81 meters per second squared. All right, that's how that looks for dropping it, throwing it down, or throwing a ball up. Now let's look at talk about slopes on these graphs. All right, the position time graph, this slope, we want to know what this slope is. We want to know what this slope is. Again, rise over run. You have delta x over delta t. That is velocity. So that slope is equal to velocity. A straight diagonal line means constant. If it's curved in any way, it means not constant velocity. Okay, which means you'd have acceleration if it's not constant. Now, here's the other thing you can tell by units. If you're starting to get confused and go, man, I don't even remember what displacement divided by time is, look at your units. Meters, I'm going to put that on the rise. That's my one on the rise. My one on the run is seconds. Oh! I've been using the meters per second all year. It's velocity. Okay? Now I'm going to velocity time, doing the same thing. I have velocity on the rise, time on the run, and that equals, go figure, it equals acceleration. So this is acceleration. Again, a straight diagonal line means constant acceleration. Again, you could have used your units. Meters per second divided by another second. Well, that's meters per second or meters per second squared, which is acceleration. Now, if you are in calculus, you go on to AP Physics C and mechanics, you're going to learn that this is the first derivative of position with respect to time. Now, when we get to and then acceleration, here, acceleration is going to be the second derivative of position with a time, but calculus is not part of your curriculum, so let's just not worry about that till you get there. But now let's look at acceleration. I want to look at areas under these. I'm going to make a constant acceleration here, and I'm going to say, hey, wait a minute, constant acceleration, but I want to see what the area is. What is area when I take the rise, which is acceleration, times the time? What does that equal? Oh, that equals velocity. And you're like, well, how did you know that? Look at this equation. If I multiply time over acceleration times time is velocity. I could also look at units. Meters per second squared times a second, 1 second on top, 1 on bottom, leaves you with meters per second when you cross those out. And that's velocity. So the area under this thing is velocity, under this acceleration time. Now, what about the area, this little triangle here under the velocity time? Okay, so you take velocity times time. Oh, that's displacement. The area under this is displacement. How do I know that? Well, let me put that back. I had displacement on top, time on bottom, or position divided by time. You multiply that time over, and you have velocity times time equals displacement. You could also do it from units, meters per second times a second. My seconds cross off, and I'm left with meters. That's displacement. So, once again, slope is velocity on a position time. Slope on a velocity time is acceleration. The area under an acceleration time is velocity. The area under a velocity time is displacement. And yes, that would be the integrals as you're taking the integrals up the other way. Derivatives down, integrals up. All right, but again, that's calculus, doesn't matter. So for right now. But here's the review. I know that was a lot of review, but I wanted to make sure you understood how you can use slope equals rise over run to use your variables on your axis to figure out what your slopes are. You can use area, that rise times run, to figure out what does the area equal. And you can always use your units as well. If you're struggling with these equations, use your units and see what you come up with. We know that if we did our units here, we came up with meters per second squared. Well, that's acceleration. We've used that all year. So the slope's acceleration. The other one thing you might want to note is do not forget on your position time, that horizontal line means you're at rest. All right, and you're like, I don't really get that. Well, if you had a meter line of 0 meters and 5 meters, what this is saying, let's say this is 5 meters right here. It says that you're staying on 5 meters this entire time. Let's say it's 5 seconds. That means you're just sitting here for 5 seconds. You're not moving, you're at rest. Okay, so remember that as well. Again, we'll have links in the description for the simple harmonic motion. There's 2 videos, and then for the video on how to translate position time to a velocity time and acceleration time if you have acceleration. So in other words, if you have some graph that looks like this, what does that look like on a velocity time, and what does it look like on an acceleration time? Because it certainly doesn't look like these. All right, so I'm linking that video as well. I hope this helps. Just wishing you the best on this upcoming AP Physics exam. You can do it. Remember, do not give up right now. You are on the home stretch. You've worked so hard. Don't give up now. Finish strong. You can do it. Thank you for watching, and happy physicsing.